In this video, we're going to introduce another concept that is sometimes critical in determining the ordering of the energy levels within a molecular orbital diagram. And so in this case, what we're going to do is we're going to compare the molecular orbital diagrams for dioxygen, which we worked on in the last video, versus that for dinitrogen. Okay, and so this is what we worked on in the previous video here. And what I'm showing here is just the top portion of the molecular orbital diagram that we showed. Remember that there are still molecular orbitals derived from the 1s orbitals, for the 1s atomic orbitals of oxygen. They're just at much lower energy. And so they are so far in energy from the 2s and 2p atomic orbitals that generate the molecular orbitals, the higher energy molecular orbitals, that they're not going to play a role for the purpose of sp orbital mixing that we're discussing. Okay, so we're really just looking at the valence shell, the MOs derived from the valence shell of the two oxygen atoms here. Okay, and so recall this is our molecular orbital diagram and the corresponding electron configuration for dioxygen. And one thing we're going to add here, speaking of energy, is we're going to add what the energy is of the atomic orbitals that generate these MOs. And so for oxygen, right, the energy for the 2s orbital is negative 32.4 electron volts, okay, while the energy for the 2p orbitals is negative 15.9 electron volts, okay. Now let's go ahead and generate the molecular orbital diagram for dinitrogen, okay. And so we're going to have our orbitals for the 2s and the 2p orbitals for nitrogen, the atomic orbitals. And so for the 2s orbital, the energy is higher in energy than the 2s orbital for the oxygen. So we're going to draw that here, where the 2s orbital is a little bit higher. 2s, okay, and that's at negative 25.6 electron volts, okay? So a good amount, about 7 electron volts difference in energy, higher in energy than the 2s orbital for oxygen, okay? Also, for nitrogen, the p orbitals are slightly higher in energy as well, right? And these are about negative 13.2, whoops. Negative 13.2 electron volts. So those are slightly higher in energy than the corresponding 2p orbitals for oxygen. Okay. Right. And then we have the same orbitals for the other nitrogen atom. Right. 2p, 2s. Okay. The configuration for the nitrogen atom is 2s2, 2p3, so we'll write in our electrons now, okay? Now notice, right, the difference in energy between the 2s and 2p orbitals for the oxygen atom versus the nitrogen atom. The difference in energy between the 2s orbitals and the 2p orbitals is smaller, okay, about 12 electron volts, the energy difference between these two, versus for the 2p and 2s orbitals of oxygen is about 16 electron volts, okay? So these are closer in energy to each other. And this is going to be important, as we'll show in a second. So qualitatively, right, if we look, we would think that the energy level diagram for the MOs constructed from these atomic orbitals should look very similar, where this is our corresponding 1 sigma, okay? This is our corresponding 1 sigma star, 2 sigma, okay? 1 pi, 2 pi, 1 pi star, 2 pi star, and 2 sigma star. Now notice, right, for instance, all of the MOs that are derived are correspondingly a little bit higher in energy than their dioxygen counterparts, because the atomic orbitals that make up these orbitals are higher in energy as well, okay? Now, what comes into play here is that this is actually not the ordering of the orbitals, okay? And so the reason for that is, let's take, for example, the 1 sigma orbital, okay? So the 1 sigma orbital we expect to be generated from the 2s atomic orbitals of nitrogen, okay? And so what happens in the case of nitrogen is that there's another orbital with the same symmetry, so sigma symmetry, at the 2 sigma, this 2 sigma energy level, okay? So these have the same symmetry, and in addition, they're very close in energy. And that yields orbital mixing. So we get orbital mixing when we have same symmetry, close in energy. Or I should say, I'm going to expand that to say the MOs are close in energy, and the symmetry, the MOs have the same symmetry, okay? So since these have the same symmetry and are close in energy, they're going to mix together. And the effect of that is, first, move this. The energy of the 1 sigma MO decreases in energy. Okay. Okay. In addition, right, because this 2 sigma MO has mixed in 1 sigma, not only is its energy decreased, but there is also p atomic orbital character in this MO now, okay? So this now is a combination of 2s and 2p character, as we call it, but the 2s character is far higher than the amount of 2p character, okay? But because 2 sigma mixed in here, so did the 1 sigma mix into the 2 sigma. And so this, while the mixing stabilized the energy of the 1 sigma MO, it's going to destabilize the energy of the 2 sigma MO, right? Which now has 2p character, but also has some 2s character. And so in this case, right, 2 sigma is going to have character of both the 2p and the 2s. The 2p is going to be much greater than the 2s character, okay? And so that has an effect on the relative ordering of the p orbital, of the MOs in the p orbital manifold, right? So instead of the 2 sigma being below the 1 pi and 2 pi, it is now higher in energy than the 1 pi and 2 pi, okay? And so other orbitals are also mixed in this, again, because the energy levels are similar. So we have similar symmetry for the 2 sigma star and the 1 sigma star. So there's also mixing between these orbitals. The 1 sigma star is stabilized a bit at the expense of the energy of the 2 sigma star, which is destabilized. And again, we have both 2s and 2p character within here. There's nothing for the pi orbitals to mix with between these manifolds. So these remain just completely constructed by the atomic 2p orbitals, okay? And this is the orbital, the relative energies of the molecular orbitals for nitrogen. Now this has an effect on how we think of the HOMO and the LUMO, right, for dinitrogen. So let's go ahead and fill up the electron configuration, right? First, right, we have 4 total electrons from 2s orbitals, 1, 2, 3, 4, and then 6 total electrons from 2p orbitals. In this case, right, by off-bow principle, the lowest energies are actually the 1 pi and the 2 pi instead of the 2 sigma, and then we fill up the 2 sigma, okay? Our bond order, right, we can determine by the number of bonding electrons, so 2, 4, 6, 8, minus the number of antibonding electrons, 2, divided by 2, which is equal to 3. That's consistent with a triple bond between dinitrogen, and that's what we expect. For instance, when we draw a Lewis dot structure of dinitrogen, we also expect a triple bond. So the molecular orbital still indicates that we have this triple bond for dinitrogen. But what's interesting here as well is what this says is that the highest occupied molecular orbital is of 2 sigma nature, okay? Whereas, for instance, in dioxygen, right, the highest occupied molecular orbitals are pi bond, have pi symmetry nature. So as we'll see later, that has some consequences in terms of reactivity. But for now, right, what we want to remember is that symmetry, molecular orbitals that have the same symmetry and are close enough in energy can mix with each other, and that can change the energy of those molecular orbitals, but also the composition of those molecular orbitals, as they will not just be, for instance, purely made from the closest energy atomic orbital, but may have some other atomic orbital character mixed into them.